You've probably heard a lot about large language models, LLMs, right? And just how powerful they are.
Oh, yeah, definitely.
But how do we actually get these AI systems to perform at their absolute best? Especially when you're talking about complex real-world problems, it's a huge challenge.
And often incredibly expensive, too.
Exactly. So today we're doing a deep dive into a really groundbreaking new approach. It fundamentally rethinks AI optimization. It lets the LLMs learn from language itself.
Right, not just sparse numbers, which could lead to some, well, unprecedented speed and efficiency gains.
Precisely. We're talking about a method called GEPA. That's GEPA, short for genetic Pareto.
Yeah, and we're drawing this from a fascinating new research paper. It's titled GPA, Reflective Prompt Evolution Can Outperform Reinforcement Learning. Quite a claim.
It really is. And it's got a heavyweight team behind it. UC Berkeley, Stanford, MIT, Databricks.
Mm-hmm.
Quite the collaboration.
Top institutions. So our mission here is to unpack why GPA seems to be such a game changer. How does it rethink optimization? And crucially, what does this mean for you, for anyone building or interacting with these AI systems?
Okay, so where should we start? Maybe with the problem GPA is trying to solve.
Yeah, good idea. So LLMs are increasingly being used in these compound AI systems. That's the term they use.
Right, these modular setups, they combine the natural language part with other tools, like maybe code execution or fetching information from a database, that kind of thing.
Exactly. And the big question is, how do you optimize the LLM part within these complex systems? How do you get it working perfectly for specific tasks?
Well, one popular method, and the paper talks about this, is reinforcement learning, specifically reinforcement learning with verifiable rewards, RLVR.
Okay.
And that includes algorithms like GRPO, Group Relative Policy Optimization.
Right, GRPO. So with GRPO, the AI gets what? Just a simple score at the end, like a number.
Yeah, basically, a scalar reward, they call it.
Well,
Just a single number after each trial or rollout, saying if it succeeded or failed overall.
hmm. My first thought reading that was, wow, that sounds like a really slow way to learn anything. Is that fair?
Oh, absolutely. That's the core issue, really. It becomes a huge bottleneck, especially for practical applications.
Okay.
These RL methods are just incredibly sample inefficient. The paper points out they typically need tens of thousands of these rollouts just to learn a new task.
Tens of thousands.
Yeah, and for full training, you might be looking at hundreds of thousands of trials. It's a lot.
Wow. Okay, so why is that inefficiency such a massive deal? I mean, if you're building or deploying these systems, is it just the compute cost?
Well, cost is a big part of it, definitely.
Mm.
Especially if your AI system needs to make, say, expensive API calls to external tools,
Right.
or if you just have a limited budget for running these powerful LLMs, which aren't cheap, or maybe you can't easily fine-tune the huge base models themselves.
Which is often the case.
Exactly. So this sample inefficiency is a major roadblock. It's kind of like trying to teach a student by just giving them a single pass or fail grade after they've spent hundreds of hours working.
With no feedback in between on why they passed or failed.
Precisely. You can imagine how slow and, frankly, frustrating that learning process would be.
Yeah, absolutely. Which I guess brings us neatly to GPA's big idea, this sort of radical concept.
Right. What if the AI could learn more like, well, more like we do?
Through understanding.
Yeah. The core insight behind GPA is that LLMs understand natural language. So maybe language itself could be a much, much richer way to learn than just getting these sparse single number rewards.
Okay, that makes intuitive sense. So how does GPA actually do that? How does it implement this idea?
Well, GPA isn't just, another optimizer algorithm. The paper calls it a reflective prompt optimizer.
Reflective, okay.
So at high level, you give it an AI system that uses LLM prompts,
Mhm.
and GPA does three key things. First, it samples what they call system-level trajectories.
Trajectory is meaning the whole process.
Exactly. It looks at everything.
Yeah.
The LLM's internal reasoning steps, any tool calls it makes, the outputs it gets back from those tools, the whole sequence.
So it's not just looking at the final answer, it's seeing the whole journey.
Right. And this is where the reflection part kicks in. It then reflects on these trajectories using natural language to figure out what went wrong or right. And crucially, why.
The why. That's the missing piece in the simple pass-fail score.
Precisely. And based on that reflection, that understanding, it proposes and tests new ways to update the prompts. And this is important. It can actually combine lessons learned from different attempts.
Okay, combining lessons, that sounds powerful.
It is. And the immediate impact they report is pretty dramatic. GPA can apparently turn just a few rollouts, way fewer than RL needs, into a really significant improvement in quality.
which means faster optimization, cheaper optimization, and more effective optimization overall.
Exactly. Better results with less effort and cost. That's the promise.
Okay, I'm sold on the promise. Let's dig into the secret sauce then. How does this reflective prompt mutation actually work? You said it goes beyond pass-fail.
Yeah, so instead of just that single scalar reward number, GPA dives deep into the natural language traces that get generated while the AI system is running.
Natural language traces, like logs, but in English.
Sort of, yeah. They capture the intermediate reasoning, the step-by-step thinking of the LLM. They capture the interactions with tools, sometimes even internal details from reward functions like compiler error messages if the task involves code.
Oh, interesting. So like really detailed operational data.
Exactly.
Yeah.
And the brilliant part is when you combine these really rich, detailed traces with the final outcome, success or failure, you suddenly have incredible diagnostic power.
You can see where it went wrong or right.
Precisely. The LLM itself can then use this information to reflect, as they say. It performs credit assignment.
Credit assignment, meaning figuring out which part caused the outcome.
Yeah, tracing back which specific bit of the prompt or which decision led to success or failure. And based on that, it can suggest really targeted updates to specific parts of the prompt or specific modules in the system.
Okay, so it's not just randomly tweaking things, it's making informed changes.
Exactly. It's like having an AI tutor watching over its shoulder, explaining why a mistake happened, and suggesting exactly how to fix it next time.
That's a great analogy. The paper had a really cool example of this, didn't it? Something about question
Oh,
answering.
yeah, the multi-hop QA example. That was fascinating. They started with a really simple initial prompt, a seed prompt.
Okay.
And the task required multiple steps, like searching for info, analyzing it, maybe searching again based on the analysis, complex stuff.
Right.
And GPA took that simple seed prompt and through this reflection process, transformed it into this highly detailed, really nuanced set of instructions, specifically for generating a much better second search query.
Wow. So it went from a general instruction to a very specific strategic piece of guidance.
All generated through language, based on reflecting on its own attempts. It's a pretty remarkable shift.
Okay, that's the reflection part. What about the second piece of the secret sauce? The Pareto-based selection. Sounds technical.
It is a bit, but the core idea is really smart. So a more naive way to optimize would be to just take the single best prompt you found so far and keep trying to tweak it.
Makes sense, right? Improve the best one.
Seems logical, but it often leads to getting stuck. You hit what's called a local optimum. You basically max out the potential of that one specific approach and waste your budget trying to squeeze out tiny improvements when a totally different approach might be much better.
Oh, okay. You get stuck in a rut.
Exactly. JPA avoids this rut using what they call its illumination strategy, based on the Pareto frontier concept.
Pareto frontier. Okay, what's that?
It's basically a collection, a set of different prompts, but it only keeps the prompts that are the best for at least one specific problem or instance it's tried. If a prompt is strictly worse than another prompt across all problems, it gets pruned, removed.
So it keeps a diverse set of potentially good solutions, ones that are good at different things.
Precisely. It maintains this diverse frontier of non-dominated solutions.
Right.
And then instead of just picking the single best one to improve, it stochastically, meaning sort of randomly but intelligently, samples from this diverse set of winning strategies.
Okay, so how does that help you, the user?
Well, it means GPAD intelligently balances exploration, trying out new, potentially very different approaches with exploitation refining the strategies that are already working well.
The classic exploration versus exploitation trade-off.
Exactly. And getting that balance right leads to more robust generalization, meaning it works well on a wider range of inputs, and continuous improvement. You ultimately get a much higher performing system within the same budget because it didn't just get stuck improving one mediocre idea.
Right. It keeps looking for better peaks instead of just climbing the nearest hill.
That's a good way to put it.
Okay, so this combination of reflection and Pareto selection sounds powerful in theory. What about the actual results? Did it work? The paper seemed pretty excited about the numbers.
Oh, definitely. The results are quite striking. GPA doesn't just, slightly improve on the older methods. It significantly outperforms the state of the art.
Okay, like compared to GRPO, the reinforcement learning method we talked about.
So on average, GPA outperforms GRPO by about 10%. And on some tasks, like one called Hot Pot QA, it was up to 19% better.
19% is a big jump.
It is. But here's the kicker. It did this while using up to 35 times fewer rollouts.
35 times fewer.
Yes. And get this. to match the best scores GRPO achieved, GAPA sometimes showed up to 78 times greater sample efficiency.
78 times. Wow, that's massive, especially if you're paying for those LM calls or tool uses.
Huge implications for cost and speed. And it wasn't just GRPO. They also compared it to another leading prompt optimizer called AMI-PRO v2.
MIPRO V2, I think that one optimizes both the instructions and few shot examples, right?
That's right. It tries to find the best combination of instructions and examples to show the model. And GPA surpassed MIPRO v2 by over 10% across different models and benchmarks.
Okay, wait. So GPA, which focuses just on optimizing the instructions through reflection,
Yep.
outperformed MIPRO V2, which optimizes both instructions and those few shot examples we used to think were so critical.
Correct. That was another really interesting finding. It more than doubled the performance gains that MIPRO2 itself had achieved over a baseline system.
That really does raise a big question, doesn't it? For years, everyone thought providing those few shot examples was almost essential for getting good performance from LLMs.
It was standard practice.
But GPA doing instruction-only optimization is beating methods that use both. Does this suggest maybe a fundamental shift in how we should be prompting these models now?
It certainly suggests that. It
Yeah.
likely points to how much better recent LLMs have gotten at understanding and following really complex instructions directly. And perhaps also their improved ability to do that kind of self-reflection that GPA leverages.
Interesting. So maybe the instructions themselves, if crafted well through reflection, are becoming powerful enough on their own.
It seems that way, at least in these experiments. And there's another practical benefit here that's really significant for your bottom line.
Oh, yeah. What's that?
The prompts that GPA generates are drastically shorter,
Shorter. How much shorter?
up to 9.2 times shorter than the prompts generated by MIPR2, which included those lengthy few-shot examples.
9 times shorter. Okay, so what does that mean for you, the person running the application?
Well, shorter prompts directly translate to lower runtime costs. Simple as that.
Because the API providers charge based on the number of input tokens, right? The length of the prompt.
Exactly. Fewer tokens in, lower bill. It also means lower latency. The model responds faster because it has less to process, and just better overall efficiency when you're serving these LM applications at scale.
So you're getting a potentially higher quality result, faster and cheaper, using a smaller, more efficient instruction manual, basically.
That's a pretty good summary, yeah. It's quite compelling. And the paper even mentions another technique, a merge strategy for GAPA.
GPA plus merge.
Yeah, which allows it to combine different optimization paths, different lineages from separate modules, potentially giving even further performance boosts. It shows how blending these strategies can work.
Okay, so GPA is great for optimizing prompts for specific tasks during a sort of training or adaptation phase, but does it have uses beyond that?
That's another exciting direction they explored. The research shows some promising early results for using GPA, not just for offline adaptation, but as an inference time search technique.
Inference time, meaning like on the fly, when the system is actually being used.
Exactly. Optimizing solutions in real time for specific, difficult problems as they come in, not just pre-optimizing for a general task.
Whoa, okay. That's a big step up in flexibility. Can you give an example?
Yeah, they apply to some really challenging code generation tasks. Things like writing low-level kernels. These are like the fundamental processing routines for specialized hardware.
Ah, like for specific graphics cards or AI chips. Super complex stuff.
Right, like AMD's XDNA2 architecture or NVIDIA V100 GPUs. These are tasks where every bit of performance counts, and writing optimal code is incredibly hard, even for humans.
So how did GPA do?
Using GPT-4o, GPA managed to achieve up to 70% vector utilization when generating kernels for NPU's neural processing units.
70% utilization.
Rev.
That sounds high.
It's very good. It means it was making really efficient use of the parallel processing capabilities of those specialized chips. And it significantly outperformed other methods they compared against.
And how does the reflection part help there? Is it reflecting on compiler output or something?
That's exactly it. This is where that detailed, rich feedback really shines. Compiler error messages, for instance, aren't just noise to GPA.
Right.
They can be used as valuable feedback to dynamically inject domain-specific knowledge. GPA can learn from the compiler errors to integrate architectural best practices directly into how it evolves the prompts to generate better code next time.
That's incredibly clever.
Yeah.
Using the tool's own feedback to guide the prompt generation.
It really is. Of course, the researchers point out limitations and areas for future work, They're looking into the boundary between this kind of prompt-based learning and traditional model weight-based learning.
Yeah, when do you tweak the prompt versus tweaking the model itself?
Right. Also, maybe adding few-shot optimization back into GPA, perhaps for certain tasks, optimizing validation set sizes for even more efficiency. And this idea of feedback engineering.
Feedback engineering.
Yeah, figuring out what kinds of feedback signals, like those compiler errors or maybe user feedback or other metrics, are the most valuable for driving this reflective learning process. What's the best information to feed back into the system?
Lots to explore still then.
Definitely. It's early days, but very promising.
So wrapping this up, our deep dive into GPI really reveals what feel like a powerful new way to optimize AI systems.
Yeah, by using language itself for reflection, using smart genetic evolution with that Pareto selection, it seems to deliver really superior performance and just astounding sample efficiency.
And the key takeaway for you, the listener, is that this isn't just some abstract academic research. It feels like a practical path toward making these complex, real-world AI workflows more adaptable.
More affordable, too, and just more effective, especially if you're working in situations where resources, time, or data are limited.
Absolutely. And it's fascinating, isn't it? We're seeing AI systems learn to almost think and improve in ways that feel quite analogous to how humans learn.
Through trial and error, reflection, figuring out why things worked or didn't, strategic refinement. Yeah, it feels very familiar.
It really does.
Right.
Which leaves us with a pretty provocative thought, I think. As AI gets better at learning from its own experience and, importantly, communicating its insights back to us in natural language, how might that fundamentally change how we interact with these machines?
How we develop them, how we collaborate with them in the future.
Exactly. It feels like it could be a really significant shift down the road, something to definitely keep an eye on.